The first talk is about transferring information across restarts in MIP, and Gregor Hendel will kick it off.
Yeah, thank you very much. So welcome back after the coffee break. It's great to see everybody like after a couple of years in person again. So very happy to be here. I'm going to present joint work with my colleagues Timo Berthold and Domenico Salvagnin about transferring information across restarts. And although the title says MIP, right, I hope you still stay tuned somehow, because I am touching some sacred topics that also like restarts or conflict analysis that might also be interesting beyond MIP. And then I brought some actually quite surprising results. So I'm hoping to sparkle some sort of vivid discussion towards the end of this talk or later. So let me introduce to you the general setting. We are trying to tackle mixed integer programs in the most generic setting, so no special problem structure that we have in mind. And as you know, state-of-the-art solvers such as Groby, Cplex, but also Express that some of you, I realize some of you haven't heard of before, but it's also a state-of-the-art MIP solver. That are usually approaching mixed integer programs by using some sort of LP-based branch and bound. This is the working horse. And as you know, nowadays, modern solvers, actually, they exhibit during the search, they use a lot of additional algorithmic components. Of course, they do pre-solving or also node pre-processing to tighten variable domains. They try to tighten the LP relaxation by using cutting plane algorithms. Whenever during the tree search, some nodes become infeasible, they can learn conflicts. We say conflicts, but some people here in this audience rather prefer no goods. So no goods to actually inform the search and actually not run into the same traps again, so to say. But after all, right, it is well known, the exponential nature of branch and bound always poses like the problem that the decisions that you take at the top of the tree are the most crucial ones, but you only have limited information available to take that decision, and you can't actually do a look ahead that really tells you how your first decisions will really affect the tree search later on. So restarts are actually a natural way to just start over, get a new chance, use the information that you already have, and just try not to make the same mistakes again, so to say. And this concept is actually well known in the SAT and CP communities, where the solvers such as Chaff or G-code, they restart the search frequently. For example, by just they transfer the conflicts, for example, that they have learned in the previous search. And then this basically represents kind of at least until purging of conflicts due to the size, right, kicks in. This also represents, so to say, the whole search that has been conducted up to that point. And now MIP solvers, they do a lot more, let's say, more work at each node, if you want. They solve LP relaxations. So a lot of information is actually encoded in that tree. So you do a much more conservative restart scheme usually. And until recently, actually, restarts were restricted to root node restarts, where just if you solve the root node, so you've done some pre-solving, you solve the root node, and then you realize, oh, due to additional techniques after solving the initial LP relaxation, more integer variables have been fixed, will then start over to actually get the benefit of a full represolve, so that you can tighten the domains and simplify the problem even further. And this, of course, can occur multiple times. And this is, I think, just standard technology in all MIP solvers. Whereas tree restarts, they are a different topic. And there you actually, like, when do you restart the tree search? There has been some work conducted by me and some colleagues a couple of years ago, where we introduced some very cheap to compute prognosis for estimating the remaining tree size. And just if this prognosis is basically says that we are doomed with the current tree, then you start over. And well, in the worst case, if you want, in the best case, if this prognosis is actually correct, then you basically do not lose much by just starting over. And still we still experimented with this on skip back in the days. And now, nowadays, we know already, this was like trade secrets for quite some time, but we know already that also all the commercial solvers actually restart. So for Express, in this particular case, like that I'm talking about, Express restarts the tree search at most once. So, and there are different goals that are kind of complementary, if you want, in restarting the search. First of all, you want to diversify the search because you know the first tree search basically did not lead anywhere. So you want to get a fresh start, probably also just by exploiting performance variability. Just doing a fresh start might actually help you. And as I said, you want to avoid the mistakes done in the previous search. But then since you are basing your restart decision kind of on an estimate how well the previous tree search was actually going, you also want, so usually the idea is, well, the techniques that you are using are not good enough to really cut off enough of the tree. So you want to intensify. You want to use more techniques that are aimed at working on the dual bounds, such as cutting planes or strong branching, for example. Intensify those techniques to actually get a grip on the remaining tree size and reduce the tree size enough to be able to solve the problem. So there are basically, when you work on tree restarts for MIP, there are 3 questions to address. First one is, of course, when to restart the search. The second is what search controls, like how do you want to actually modify the search behavior before and after the restart? And these, however, are still considered trade secrets. So you can't really give a scientific talk about those, but instead we will focus on the public part of those 3 questions, which is what information to actually carry over. Yes, please.
When you do a tree restart, do you assume you're doing full tree solving again or not?
Next slide, Chris. So how do we actually perform? How do we perform such a tree restart? So here actually, this just imagine you are at some point of your first tree search. I don't know if this is actually very visible. Yeah, it is visible, right? There are some trees, some nodes you haven't explored yet, you are not fully done. And now you decide, well, this tree search is not going well. So, and what you then do is, well, you perform the tree restart, which means you basically throw away the tree if you want, and you conduct a full Represolve, and then which hopefully leads to a much smaller tree, as in this 3-node example. So there are some things that you would naturally transfer in this situation. Those are primal bounds and solutions, the dual bound, and also you can actually transfer the Represolved LP basis to warm start the dual simplex after the Represolve. Yes?
What is different between the first and the second pre-solve in terms of inputs?
So first of all, we will get to that, and the global information that we are transferring will be part of it. But so first of all, you are basing your pre-solve on the already pre-solved problem, right? You can basically do further domain reductions. It is not like you start again from the original problem that the user has input. So, and this is now actually, this is like the goal of this talk is to discuss different aspects, different pieces of global information. What are we looking at explicitly? Those are conflict clauses, the implication graph that you learned through probing, cutting planes, and pseudo-costs or branching history. And like I will now explain, oops, sorry. I will now explain those in more detail and the technical difficulties or the technical challenges in transferring them. So let's first talk about the general setup. Well, as you know, Presolve actually transforms the original MIP into an equivalent MIP where, well, I just added primes here for the notation. When we now think about a Represolve, actually we can think of the already pre-solved problem as the new original problem, plus the user gave us some information from outside, right? For example, some cutting planes. This is even possible through modern solver APIs, right? To have a pool of cutting planes that could already be used, so to say, for the search from the user. So we don't need to worry about, well, pre-solve plus represolve, but we now just need to worry about the pre-solved problem, so to say, in notation. And now, what are the states that a variable can be in after pre-solve? So the original variables, if you want, that come from the previous search, they could, after the represolve, they could now be fixed to a constant. So they could also be mapped to a potentially different variable index. They are basically still active columns, if you want, of the remaining problem, or they could become unmappable for several reasons for our purposes. Unmappable, the most likely explanation is that a variable is now expressed. It was basically deleted or eliminated from the problem because it is expressed by other variables, like in some form of aggregation, for example. So how do we transfer cutting planes in Express between or across the Represolve? Well, here we actually use the cutting planes during the Represolve. So this is one form of information that actually adds to the Represolve, if you want. So we add them just as rows to the matrix, and then we perform the Represolve. And afterwards, we actually extract those cutting planes from the matrix back into the global cut pool and treat them as cuts again. And so the advantages of this approach are that we have potential additional Represolve reductions, and we can warm start the root node with already existing and proven to be useful cutting planes. Micha?
You do a parallel constraint reduction based on new cuts that you added to your model, and you might use original constraints. And if you extract the cuts again, then your problem may create solutions that are not valid for the original problem. How do you, or what do you do then?
So we protect basically, there are some operations that are no longer possible then, and we protect basically that this happens explicitly. Transferring pseudo-costs. So pseudo-costs, now there's always like a clash of terminology. Pseudo-costs are actually they are an estimate that is based on branching history. You record branching history on the variables. So let's say we transfer branching history. And well, how do we perform this? We actually, we found that through preliminary experiments that it is best actually performance-wise to treat the collected branching history just as a single observation after the Represolve. So when the search starts, it will still do some more strong branching. It will not consider the variables as reliable, for example, already, but it will basically, use that information to launch the search, but then later this information will weigh out when we see more information during the current run. And we actually also found that it was beneficial to discard the branching history completely if the problem changes too much as measured by problem size. So just if the presolve changed too much, the represolve, then we discard this branching information where the relative limits are 10% columns and non-zeros or 5% of the rows. If any of those limits is exceeded, we discard the branching history. We transfer conflict clauses. So conflict clauses, you may well know, clauses are of the following form. Those are basically disjunctions of these literals that either involve the upper or the lower bound of the variables, and they represent constraints that, well, any feasible solution has to satisfy. And during the Represolve, some things can happen. Some literals of fixed variables, for example, I mean, all the literals of fixed variables can be removed, and they might already lead to a certain clause being redundant after the Represolve, because now this bound change is trivially, this literal is trivially satisfied. Yeah, but if the particular literal is not satisfied, then you can still remove it from a fixed, about a fixed variable. And however, an empty conflict after this kind of removal procedure will actually prove infeasibility of the Represolved model. And just if you end up with a single bound change, then this becomes a global bound change on the remaining variable. And the last piece of information that we are discussing, those are implications between variables. Also, this is also known as the variable bound graph. And there, more or less, the transfer works exactly the same as for conflicts. If one of the involved variables, for example, became unmappable during the Represolve, then the whole implication about it between two variables is discarded. And if both variables are fixed, the implication either proves infeasibility directly, or it becomes redundant in the Represolved space. And if one variable is fixed, we turn the implication again, as for conflicts, into a global bound change. And only in the case where both variables survive, then we transfer this implication. So this is the technical background. Now let's see some numbers. We performed experiments with Express 813. This is our October version of Express. We performed it on our internal test set that has 619 MIP problems, where we consider always 3 permutations. This is our default testing methodology. We consider the default and 2 cyclic permutations of each problem to also somehow, to increase the test set size and have the results less prone to performance variability. We use a 4-hour time limit. And here, the first slide shows the combined results. On the left, this is the no transfer setting, and the right is the transfer setting. The transfer setting is also the default of Express. So what you see is that overall on the entire test set, you see that to the right, the time improvement is 3% and the node improvement is 9% when we enable the transfer of information. However, this whole test set is actually quite, well, it consists of very many different instances that also many of them might, for example, solve during the root node. So this is for us like the standard to look at first, but then we are also interested in the affected instances. And affected are basically a third of this test set, and there the results are more pronounced because, well, those are the ones that actually benefit or don't benefit from the algorithmic changes that we introduce through the transfer. And so there, the time and node improvements are much more pronounced. So 3% overall, 7% overall time improvement. And on the harder of the brackets that we consider, I should introduce the brackets. This is instances that both versions, that at least one of the versions could solve, and the slower of the two took, for example, 10 or 100 seconds. So this actually reduces the overall test sets to harder instances of interest. Yes?
And here number of nodes is total number of nodes across the restarts?
Yes.
And no transfer means restart, but don't transfer or don't restart?
No, it means, so before the actual tree restart, right, nothing actually happens. And then we actually, so yeah, the no transfer setting will restart, but it will not transfer information. And I see I have 5 minutes left. Thank you very much. So the results for cuts are more or less in the same ballpark. What is noticeable about cuts, let's just look immediately at the affected instances. what's noticeable is that there is a consistent time improvement, but there is actually a very huge improvement in the number of nodes. And this, I mean, this is the usual intuition that you have about cutting planes, that they actually, just their presence in the LP, of course, slows down the LP solves, but they help a lot in reducing the search tree size. The results for pseudo-costs. Now here, I would like just to point out that the affected instances here, whereas for cuts, basically, you see that out of the 670 that were affected in total, 659 are affected by cuts. So cuts are everywhere. Whereas for pseudo-costs, fewer instances are actually affected, and this is also due to the filtering that we did, where if the Represolve changes the problem too much, we start from scratch. So this means our pseudo-cost transfer is actually affecting fewer instances. But on those where it does, it actually leads to a nice performance improvement of 5 or even 6% in time, and 4 or 3% in nodes. And now the surprising result is, now you were thinking that this just continues, but it doesn't. It's actually, and now this actually came as a surprise to us, that conflicts do not yield. The transfer of conflicts in our version actually did not lead to it led to actually a substantial performance degradation in time and nodes. And the same actually happens for the implication graph. The implication graph there, the results, the deterioration is less harsh than for conflicts, but still the implication graph actually transferring these implications actually led to a slowdown in our case. And now, so we were trying some things where we actually thought, especially about conflicts, that could try to explain those results. One of the most straightforward explanations for this could be that, well, once the conflict pool is full, new conflicts that arrive might probably more recent conflicts, because recency of conflicts actually plays an important role. And once the conflict pool is full and no new conflicts can enter the pool, I mean, we have a purging mechanism that is based on length. So that you have the most global conflicts always in the pool present, so that they have a high chance to actually propagate further. And so one algorithmic changes that we did in the direction like increasing the pool size, for example, after restart, just to mix and match the best conflicts from both times. This is still at the moment, I can't report actually better results here. So this is actually what I'm really interested in here now. If I find you, if you find me over coffee, for example, then we could have a discussion about why, for example, the transfer of conflicts, what can be the reason here. I've also seen some preliminary results on skip. And if skip is very conflict-based, if you disable the conflicts there, the transfer, then you have a slowdown of 50%. So this would be something that many of you would actually just nod and agree with. Whereas here in our case, we are still looking for new explanations why this actually leads to a slowdown. So as a conclusion and outlook, so overall, we actually got a significant speed up from transferring global information altogether. However, some of the pieces of information, such as conflicts, just using this information ad hoc, it does not always pay off. Also for the pseudo-costs or for the branching history, we needed to do some work actually and introduce those limits to actually make it work in our case. And so, but about conflicts and implications, there's simply more research needed to fully use the potential that we have there. And future work in this direction, in the direction of transferring global information, might also work on global bound changes that are what I call inherent in the first tree. So just if a variable is implicitly bounded already because all the open nodes just want to see it at 0, then this can be transferred as a global bound change. Or other pieces of global information might be cliques or the Farkas pool. So thank you very much.
Is it possible that the implication is preventing branching on some branch and bound variables, like on some decision variables? Is it like limiting the candidates that you could have by kind of pre-solving them away?
Yeah, but pre-solving some of the candidates away would just mean that you combinatorially, you know already, okay, this variable will just have one value, right? So actually you would think that from this additional domain propagation that the implication graph gives you, you should actually like be able to focus on the actual variables of interest.
So it's not like replacing that variable. It's saying like this variable is equal to 8 times a set of other variables and replacing it.
No, the implication graph will really be like, so it will use some sort of linear relationship between the bounds of variables. So if this variable is now reduced, let's say its upper bound to 8, this other variable, it has already, it was shown that this variable must be set to 0 or something like this. This is the implications. The other thing that you mentioned, these are eliminations that happen during pre-solve where columns are removed because they are expressed by in form of other variables.
Time for one more question.
I get to pick?
Yes.
So you have asked already, so let's go with Peter now.
So I'm just an intuition in parallel SAT solving, which is a bit the same because there's different search trees happening in the different parallel things. They are very restricted in the nodes that they crop or conflicts, that they move from one to the other because conflicts are very local. But the other thing is it might be an interaction with your cut pool, because if you're not measuring how active this cut has been recently and throwing it away quickly, then I can imagine that these old nodes from this previous tree are essentially irrelevant, and unless you quickly eliminate them, you kind of take up space which could be used.
Yeah, so in the parallel setting, we have no good notion of recency in the sense that so you can't just increment counters, because once you merge the information from different threads, the recency is kind of lost.
Let's thank Gregor again.